Okay, guys, so for part 2 of the graphing rational functions, we're gonna talk about how to find a couple other pieces that we didn't do the other day. So we talked about how to find intercepts, vertical asymptotes, horizontal asymptotes, and now we're going to introduce a couple other things. So one of the things, when we talked about domain, we said that the vertical asymptotes would be anywhere the denominator is 0, but the top isn't. But when you talk about domain, any zeros of the denominator are considered values that can't be in the domain. So for the values that do cancel out, that's going to be represented by a hole in the graph, which is just kind of like an open circle. So if you were connecting graphs, you would just put a little circle in the part where it's supposed to be connected. So how to find them algebraically? All right, this is what we would do. So if the numerator and denominator do have a common factor, which basically means you could get 0 in the top and the bottom, and let's say that common factor is x minus h, then the graph will have a hole at this h value. All right, so x minus h, which is basically the 0 of this linear function. And that would be the x coordinate. To find the y coordinate here, the f of h, you would have to find the value of the function after the common factor cancels out. So we're going to look at an example so that you can see how to find the coordinates of the hole. So let's start with this rational function. So we've got our x's on top and the bottom, and if we were asked to find vertical or horizontal asymptotes, we could do that, intercepts as well. But this graph actually has a hole as well. So what we want to do is we want to put it in factored form. So we're going to factor the top by taking out a 2. We'll be left with x squared minus 4, which is also difference of squares, so we would factor that as well. And then on the bottom, we've got this trinomial that we're going to factor into x plus 4, x plus 2. All right, so this is our factored form of the rational, which is helpful when you're trying to find certain things like domain and asymptotes and things like that. But if we notice, the factor x plus 2 occurs on the top and the bottom. So there are two discontinuities for our graph, x equals negative 4 and x equals negative 2. But only one of them is actually a vertical asymptote. Because this would cancel, x equals negative 4 is the only one that's a vertical asymptote. What happens at x equals negative 2, right? So when we reduce this, we still have to put this domain restriction in, and that means that that's where there's going to be a hole. All right, so it's not a vertical asymptote. X equals negative 4 would be the vertical asymptote. X equals negative 2 would be where there's a hole. So that's the x coordinate. To find the y coordinate of the hole, we have to plug the negative 2 back into this function. We can't plug it back into any of the previous ones because we would just get 0 over 0, which is undefined. So we want to plug it in here, and that will give us the hole that occurs at negative 2, negative 4. So when we get to sketching it, this is something that we'd have to identify so that when we sketch, we'd have to put a hole at negative 2, negative 4. All right. So vertical asymptote at x equals negative 4, but there are discontinuities at negative 4 and negative 2. This one's a vertical asymptote. This one's a hole. Okay, so that's how you would find holes in the graph. The other thing that we can say is that when we had horizontal asymptotes, we had 3 rules. We had that if the degree of the bottom was bigger, there was a horizontal asymptote at y equals 0. If the degrees were equal, we had to take the leading coefficient of the top over the leading coefficient of the bottom. And if the degree of the top was bigger, we didn't have a horizontal asymptote. However, there is a special case where you can have something called a slant asymptote. Okay, and this occurs when the degree of the numerator is exactly 1 greater or 1 more than the degree of the denominator. And to find that slant asymptote, we have to use long division. Okay, so we're going to take a break. I'm going to go on to the next video and we can see the example of this because it's a little bit longer, and then you'll get the assignment.